All right. So this time I remembered to send out the invitations, didn't I? Very good. So, all right. Anyway, so let's carry on with chapter 7, our discussion about the normal distribution. And just a few quick reminders. We looked at the properties of the normal distribution. And well, before we even did that, we noted that, all right, let me just step back here for a second. First of all, the normal distribution is a continuous distribution, which means that it describes situations where there could be potentially an infinite number of different values. Like, here's a good example. Let me just throw another one in here. Suppose, and this is more an applied application that you might actually run into. Suppose that returns to a portfolio of stocks are normally distributed. Then let X represent the returns. And so we could use the normal distribution to calculate probabilities. For example, we could then determine probabilities such as the probability that the returns to the portfolios will be greater than 10% next year. All right, so this is exactly the kind of thing that you might want to know with a portfolio of stocks. This could be for a Wall Street manager, or it could be for you individually as a stockholder, which of course at some point down the road you probably will be. And it's actually not that uncommon to assume that stock returns are normally distributed. In practice, they are very close to being normal. They're not exactly normal, but they're close enough that we often do a lot of empirical studies with stocks based on the assumption that they're normally distributed, so that we can ask questions about what kind of returns we're likely to get. And in that way, that makes it easier to choose different stocks that you might want to add to your portfolio. So without that assumption of normality, that would make things a lot harder. Okay, so in other words, in a lot of cases, even if the data are not really 100% normal, it often is the case that they're close enough that we can do a good job calculating probabilities. And in many, many applications, this is extremely helpful information. So like I was saying yesterday, the normal distribution shows up in a lot of different applications, not just in business, not just in finance, not just in economics, but other disciplines like biology. For example, if a pharmaceutical company is developing a new drug and they're trying to figure out the likelihood that it cures a certain disease, they may end up needing to use statistics to help them understand the likelihood that each of these drugs is effective. Or else, imagine in psychology, suppose that a psychologist is wondering if, people, how they react, let's say, to bad news, and they want to do studies about this, or how do they react to coming back from the COVID, and a lot of their research does ultimately depend on assumptions about the statistical properties of their data, and frequently that assumption includes normality. So it's a very important idea. In fact, if you remember one thing from this class, I would say this is the one you should hang on to, because it's the one you're most likely to run into in one of your other classes, the normal distribution. Now, where the name comes from, that I'm not so sure about. It's kind of a lot of the names of these distributions are kind of lost in the mists of time, but we do know a lot of the statisticians who worked on this normal distribution. And they all have their own interesting histories, which we don't have time to get into now. But the history of statistics is actually quite interesting. If you ever had the time to read about it, you'd see that a lot of the people who developed these results were themselves quite interesting characters. So anyway, so continuous means there's an infinite number of possibilities. So, and one more thing I forgot to mention up here. It makes sense that the returns to stocks could be normally distributed because they are percentages which can have a fractional component. And so therefore, there's an infinite number of possible returns to a portfolio of stocks. All right. So now that doesn't prove anything by itself, but it does mean that the returns to stocks definitely follow some continuous distribution. And it turns out to be most likely the normal distribution. All right, so I introduced these concepts with a histogram, a very simple one where we only had 5 possible outcomes of whatever process this is. And you can see that this is a valid distribution, but this is a discrete random variable x because we only have a finite number of possible values. If we have an infinite number of possibilities, we can't really realistically create a histogram out of those different values of x. So what we end up with is a curve. So there's what we have to visualize is that this curve actually represents the tops of an infinite number of bars all squeezed together. It's like imagine an infinite number of bars all crammed together. This curve is actually just the top of each of those bars. So the curve itself is smooth and continuous because there's an infinite number of bars here. And so with a continuous distribution, we don't actually calculate individual probabilities, but we calculate ranges of probabilities. So we saw a lot of that yesterday. Here, for example, we would not calculate the probability that x equals 2 or 3 because that would simply be 0. Instead, we might ask ourselves, what's the probability that x is between 2 and 3? All right, and that we can certainly do with our continuous distributions. And we note also that, as you would expect from the axioms of probability, the area under this curve is 1. Okay, it has to be because it represents probabilities. And we know that the sum of all the probabilities has to equal 1 according to the axioms of probability. All right, so we jumped ahead here. Let me jump ahead here a little bit. And we introduced the normal distribution, which we've seen many times now. It is a bell-shaped curve. It has the mean is in the center, and it is symmetrical about the mean, which simply means the area on the left and the area on the right are mirror images of each other. Which means, and we saw later on in the slides what that indicates as far as probabilities are concerned. But those are really the key details. One last thing too, the tails of this distribution, if you notice, they don't stop. They go all the way out to positive infinity on the upside and all the way down to negative infinity on the bottom side. So interestingly enough, even though this curve actually has infinite tails, the area is still equal to 1 based on the way it's been defined. And so the curve here represents this function. This is simply a picture of this. In fact, if you had really high-powered graphing software, you would type in that function and you'd see it turns back, or it gives you back this wonderful bell-shaped curve. Now, if you look at the formula carefully, as I said yesterday, here we have pi, the actual Greek letter pi, 3.141. E is the constant 2.71828, which we saw in the lambda, the Poisson formula. The key detail here, though, is the values of mu and sigma. Okay, so remember, mu is the mean, sigma is the standard deviation. It is these two values that determine the key properties of the normal distribution. Specifically, the location and the spread. Okay, so for example, here's two normal distributions with the same standard deviation but different means. And you can see the only way that they're different is where they're actually located. The means are in different locations. And so the means are telling me where these curves are located on the real number line. The shapes are the same though, because the standard deviations are the same. But on the other hand, if we had this two distributions with the same mean but two different standard deviations, you can see they're located in the same place, but the one with the smaller standard deviation is quite tall. Most of the area is in the center, and there's very little area in these tails. Whereas with the high standard deviation, it's the other way around. It's like here's the height. You can see it doesn't go up very high, but it spreads out quite a bit. In fact, the best analogy I can think of here is imagine the first one, the tall one, is a big, big scoop of ice cream. And the second one is what that ice cream would look like if you let it sit on the counter for a while. It starts to melt and it gets smaller and smaller, but it spreads out more and more. So anyway, so this shows us how we can imagine or visualize how the mean and the standard deviation uniquely characterize this normal distribution. Now, I did want to quickly review here With a binomial distribution, we did say that the distribution is uniquely characterized by n and pi. Remember, n is the number of trials, pi is the probability of success. If we know these two values, we know everything we need to know about that distribution. With Poisson, there's only a single value that we need to know, and that's lambda. All right, if we know lambda, we know everything we need to know about the distribution. And in fact, we saw several histograms that illustrated exactly what this means. So to continue on to the normal distribution, well, you can see that in this case, the normal distribution is characterized by the mean and the standard deviation. Okay, and also these values are referred to as parameters. Okay, so in other words, when you see the word parameter, it means the values that uniquely characterize a probability distribution. Now, if you notice that they all have either one or two parameters, there do exist probability distributions that have more, but they're horribly complicated, and so we won't be using those here, but they do exist. Okay, there's nothing to stop a distribution from having 3 or more parameters, but we just don't need them here. Now, you might also recall that we chose one particular normal distribution, which turns out to be the most important of them all, which we call the standard normal. And it has the very convenient properties that the mean is 0 and the standard deviation is 1. And the tables that we've been looking at are based on the assumption that we're looking at the standard normal distribution. If we have a different distribution, we can make a conversion to use the tables, but the tables themselves are based on this particular distribution. And we'll see that we'll get a lot of use out of it. Yes, the other thing we mentioned here is that we're going to use the letter Z from now on to represent the standard normal distribution. That's standard practice in statistics. X can be anything. Z is the one that's reserved just for the standard normal distribution. And because of that, the number or the value of Z is often called a Z-score. All right, so you see that sometimes, Z-score, because it represents a value taken from the standard normal distribution. All right, so here's another graph. This was done in Excel, and you can see that the center of the distribution is 0. Okay, and then the tails fall off very quickly. And you can see there's very, very little area in these tails once we get past. Actually, let me get this out of here so you can see it better. If you notice, there's +3. Actually, I'm going to leave those in there. Here's +3. Now, remember what this means. This is the mean. This is 1 standard deviation above the mean. This is 2 above the mean. And this is 3. This is 1 below, 2 below, and 3 below. So we saw that this area within 3 standard deviations of the mean, this represents almost the entire distribution. Okay, or 99.7% of the total. So the area outside of these ranges is extremely, and I mean extremely small. So that means these are events that happen extremely infrequently. It's like, imagine yourself seeing on the street, walking around, a basketball player who's 7'2" tall. That happens extremely infrequently. So his height would almost certainly put him up here in this area, way above, even past mu +3 standard deviations. That's an extremely unlikely event. In fact, it could be thought of as an outlier. Okay, so the curve, most of the areas within these 3 standard deviations In fact, if you look at the table, let me just go get it for you. I almost forgot to open these up. If you look at the table, let's look at the positive table. It only goes up to 3. Actually, it's 3.09. Why do they chop it off at 3.09? Because you can see the area past 3.09 is almost 0. So for all practical purposes, these are the only values that are relevant. Okay. And that's one of the important properties of the normal distribution. All right. So we did go through these graphs. Remember, within one standard deviation was approximately 68% of the total, or roughly 2/3. Between two standard deviations is approximately 95.44%. And within 3 standard deviations, as I said before, about 99.7%. The rest of the area outside of that is almost 0. It's very, very close to 0. So we can't just ignore it, but it's so tiny. That's one of the reasons, by the way, why this whole curve actually has an area of 1, because the majority of it is focused right in here. These tails that go out to infinity their area is so tiny that it doesn't go beyond 1, the grand total. All right, then we started doing the tables. Now the tables are cumulative probabilities. So for example, to look at the probability that z is less than or equal to 1, we break it up into 2 parts. 1.0 comes from here, the 0.00 comes from here, and we end up with 84.13%. Now, we did have an example here with a normal distribution that's not standard normal, just to illustrate what we've just done. And we were told that the mean is 80, the scores of the exam are normal, the mean is 80, the standard deviation is 8, which implies that a score of 88 is 1 standard deviation above the mean. Okay, 80 plus 8. What's the likelihood of getting a score of 88 in this case? Well, this is the equivalent of asking, let me see if I can sneak this in here. The probability of getting a score of 88 or below is the same as the probability of getting a z-score less than or equal to 1. They represent the same thing. And in fact, I showed that on the graph on the next page. So you've got up here on the top the grades with a mean of 80 and standard deviation of 8. So score of 80 corresponds to 0 down here with the standard normal. So a score of 88, as you can see, corresponds to 1, and a 72 represents -1. So if I wanted to know the probability of getting less than or equal to 72, I would go to the chart, the negative chart, and look for -1. In fact, why don't we do that right now? So getting a score of 72 or below has a probability of, okay, I'm trying to make it bigger. Here we go. There we go, -1. 0.1587. So in other words, if you got a 72, you're in the bottom, basically the bottom 16% of the class, which is not too cool. All right. So in other words, you can see that any probability we need to calculate, if it's not a standard normal distribution, it doesn't matter. We can easily convert it into that form using this formula over here, which I think it's very important to highlight this a little bit. Just so you don't overlook it. You never know when it might pop up in an exam, okay, or a homework. Okay. Oh, you know what that reminds me? Before I completely forget, remember last week we did the chapter set for problem set for chapters 3 and 5 this week, because we'll be done with chapter 7 this morning. What I would like you to do is the chapters 6 and 7 problem sets this week. All right. 6 was the binomial and Poisson distributions. And 7, of course, is the normal distribution. By the time we're done today, you'll have plenty of knowledge of these two topics. So you'll have no trouble doing the chapter 6 and 7 problem sets by next Monday. So in fact, I am so, I just want to make sure that everybody gets the message that I'm going to go over to Moodle right now and add an announcement. Let's see, where are the announcements? There it is. There it is. All right, I'm going to put it in here right now, so there's no doubt in anybody's mind. And also, I apologize for the delay in getting your first set corrected. I'll take care of those between now and next Monday. Okay. It's been one of those weeks, so I haven't had time to correct them, but I will, don't you worry. So second assignment. So the chapter 6 and 7 problem sets are due on Monday. That would be the 21st. All right, that's all we need to say. Ta-da! All right, and by the way, as long as we're in Moodle, let me just show you, I've added some new good stuff for you. Right now, we're all caught up. So what I did yesterday, remember I added a bunch of new discussion about calculating probabilities. That appears here in what I call chapter 6 with notes 61521. So in other words, this is the original PowerPoint presentation. What you're seeing here is the same thing with all my handwritten notes, so that everything we went over is in here, including that extra discussion we had yesterday about how to calculate different types of probabilities. So it's all there. The problem set is here for 6. And I moved these down to this week. 7 is done. We're going to be done today. I'll post whatever notes I create today. There's the problem sets. You're all set. Here's your tables if you want to use them. And then I've sneaked in there chapter 8, which we'll at least touch on today. And you'll be happy to hear that chapter 8 is entirely based on the normal distribution. So in other words, everything we just learned will be applicable in chapter 8. Okay. Now, after today, we'll be halfway through the course. So I did mention yesterday, in fact, maybe I'll throw that in here as another announcement. Midterm. The midterm will be based on chapters. I think it would make sense to have it be based on 3, 5, 6, and 7. Yeah, that sounds good. I normally, during the school year, I have 2 midterms. That's why I have to think about this. But during the summer, we really don't have time to mess around with 2 midterms. So we'll have those 4 chapters. We will review these chapters next week. I don't know exactly when. I will post what I call a sample midterm for everyone to review. Oh, in time for the weekend, that is, so you can look at it during the weekend. You notice how I'm assuming that you spend your weekends working on statistics. Well, I hope that's a valid assumption, at least part of the weekend. So anyway, so then that week, sometime next week, maybe Tuesday, maybe Wednesday, we'll figure it out. We'll go over the sample midterm. We'll probably do it on Tuesday, because that way, in case it spills over to a second class, we can finish it up on Wednesday. And that way I can also give you the exam over that weekend, although I'll probably give you more time to get that done, because it might take a while. So we'll talk about this again next week. All right, so we will review the sample midterm on Tuesday and possibly Wednesday so that you can work on the midterm for at least a week. Okay, so in other words, for this is so important. I'll give you at least a week, maybe more. We'll figure that out too. Okay. Now, as long as we're on the topic of announcements, now here's something bizarre that I wasn't expecting. Week 4. Now, I had no idea this was going to happen. During the 4th week of class, which is the week of, I think, June 28th. Let's see. Yes, no, the 28th. Okay. Unfortunately, one of my other schools kind of crossed me up a little bit with their scheduling. So we will have to start a little earlier than usual. So, but I will post announcements about that to remind you of the time change. I didn't mean for this to happen, but I got thrown completely off by one of my other schools. They started their summer session a week earlier than they normally do, and all of a sudden I've got a conflict. So it's not much of a change. We'll probably have to start a little early, maybe an hour at the most. I don't want to get you up too early, but just for that 1 week, it can't really be helped because we obviously can't waste any time. So I just want to throw that out there right now. All right, so that should take care of all the announcements. So let's get back to the work. Yeah, that's the important part, right? We all want to know what's going on with this normal distribution. So I've colored this in just to show you how important it is. And so we've done quite a few of these examples. So we don't need to go nuts practicing any more of them, although there is a problem coming up that I'd like us to do together. The only thing that I want you to remember is these properties. First, the entire curve has an area of 1. The area to below the mean is a half, as is the area above. And that's due to the symmetry of the curve. And so if you need to calculate a greater than or equal to probability, you can do it as, I forgot this was on. This is good. 1 minus the probability that it's less than or equal to that value. So here in this case, you're seeing if I needed to know the probability that z is greater than or equal to 1.08, that's not in the table. What I can do, though, is calculate 1 minus the probability that z is less than or equal to 1.08, and the final answer will be 0.1401. In other words, this pink region is what we really wanted. The black region is what's actually on the table. So you can see, though, they do add up to 1. So if I know one, I know the other. And that's one of the nice things about the property that the entire curve has an area of 1. All right. And then the in-between probabilities, you're actually taking the differences between them. So, for example, we wanted to know the probability that z is between 0 and 1 and 2, rather. And so the way to do that is to calculate the cumulative probability that z is less than or equal to 2, and then subtract the cumulative probability that it's less than or equal to 1. And that turned out to be 1359. I should say 0.1359. All right, so that should take care of them all. All right, and here's our famous formula, z equals x minus mu over sigma. Now, with all that being said, we're going to start a new problem now. Suppose that the annual return to a stock is normally distributed with a mean of 5%, and a standard deviation of 2%. Now, for these types of problems, I just want to point out, your best bet is to not use the actual percentages. I would recommend that you write this as a decimal. It just is easier to avoid mistakes. Much easier, as a matter of fact. Now, with that information in hand, we can now calculate any probability that we choose. For example, all right, I'll repeat these up here. Oops, I've got it backwards here. The mean is 5, and the standard deviation is 2. Now, here we're looking for the probability that x is less than or equal to 0.04. Now, of course, the tables that we've been using are for the standard normal distribution, so we have to make a conversion before we go to the tables. And of course, that's our favorite formula. So now the tables are on Moodle. You should have downloaded them by now. I hope you have them right in front of you. So what I'd like you to do is take part A, convert that into a standard normal form, and then calculate the appropriate probability from the table. All right, so I'll give you a minute to work on that. It's not that complicated, but we definitely need the practice. Okay, so I'll give you a minute and then see what you can come up with. All right. So here's the formula, which means you're subtracting the mean of a half, sorry, not a half, 0.05, 5% divided by the standard deviation of 2%. And so what you've actually got here is equivalent to asking what's the probability that z is less than or equal to negative 0.05. All right, now that's easy because it's right on the table. So for that one, remember the way the table is structured, there's always 3 values. So negative 0.50 can be written as negative 0.5 minus 0.00. So let's get the table out and see how that would be done. I'll get rid of these. Negative 0.5 has to come from here. And although you can't see it way at the top here, this is the column for 0.00. And so we find ourselves at the intersection with 0.3085. So that means there's a 30.85% chance that the return to your stock will be 4% or less. Very good. Now that was an easy one because it's a less than or equal to probability. What do we do with the other two? All right, well, we already know how to do this, so why don't we go back and try B, 8% or more? So I showed you the trick for what to do with or more, which we did yesterday and we reviewed it this morning. So why don't you go ahead and see what you can do with the probability that X is greater than or equal to 8%. All right, let's do it. So first of all, you of course apply that formula, Z equals X minus mu over sigma. And remember, the mu is here and the sigma is here. So this is the equivalent of asking what's the probability that Z is greater than or equal to 1.5. You also remember that the strategy for doing this with a table is to rewrite it as 1 minus the probability that Z is less than or equal to 1.5. So if you go to the table and look for 1.5, the positive table, how do we find it? Oh, here we go. Here's the 1.5. Here's the 0.00. And that gives me 0.9332. And that is actually this unshaded area. That's not what I want, is it? No. So these two, remember, they have to add up to 1. So this one must be 0.0668. And that, of course, is the final answer. That's how it's done. Okay, so remember, with greater than or equal to probabilities, the best bet is to rearrange it and solve it like this. Oh, I did have a separate graph here. That's cool. All right. So remember, again, this is what you looked up in the table. But this is what we wanted to know right here. All right, so then in part C, we have another challenge. It's an in-between problem. What do we do with these cases? Oh, that's right. Well, I'm not going to remind you. I hope you remember, but if not, you can look at your notes what to do with an in-between problem like this. So go ahead and take a minute and see what you can come up with. All right, so let's see how that worked out. So again, you're applying this formula where the mean is 5, the standard deviation is 2. So that means you end up with this result. We're trying to find the probability that z is somewhere between 1 and -0.5. So you might remember that in a case like this, what you're actually going to do is go to the tables. I'll rewrite this as 1.00 because that's how you'll look it up in the table. But when you look these up, all you have to do is subtract one from the other, and you'll end up with 0.5328. Okay. Now, by the way, if you get these backwards, you'll just get the negative of the correct answer. It just means you got them in the wrong order. Not a problem. Just reverse them. All right. Now, it's finally time to let you in on a big secret. A lot of what we've been doing here is available on the calculators. How does that work, though? All right, so I'm going to show you how you could have done a lot of these without the tables. Now, the tables are important, but I mean, the reality is that since we have the calculators, we don't really need them, at least not very often. So what you have to do is, now this is a menu that you're already familiar with. We've seen it the other day, second VARS. This is the one we used to come up with binomial PDF and Poisson PDF. Now, instead, we're looking for normal CDF. By the way, let me just make a note here. Don't use normal PDF. That's because this is a continuous distribution. With binomial, we use PDF except when it was a cumulative probability. With Poisson, we use PDF unless it was a cumulative probability. Here, don't use PDF at all. Always use CDF. All right, make sure you remember that. If you're going to use the calculator for the normal distribution, always, always, always use normal CDF. It sounds backwards, but it's not. This is because it's a continuous distribution. Normal PDF will give us a result that we don't need. We want the probability of being less than or equal to a certain value, and the way to get it is here. Now, there's 4 things you'll have to enter here. Lower, and we'll explain that in a second, upper, and then the mean of the distribution. Let me just get that symbol in there. And the standard deviation. All right, that's the basic setup. Now, if you notice the lower, this is the lower limit of the interval. And of course, that implies that this is the upper limit. Remember, we're only doing intervals with a normal distribution. Now, there's just one quirky thing we have to watch out for. All right, so as an example, suppose we need to know or need to calculate the probability that z is less than or equal to 1. Now, we've already done this one, so we already know that the answer is 0.8413. But how would you get it with this calculator? Let's see if we got room here. All right, this is better. So it's second vars, normal CDF. Now, what I want to point out to you is this. When you calculate the probability of Z being less than or equal to 1, what you're actually doing is this. You're actually doing everything from 1 down to negative infinity. Okay, we didn't specifically mention that before because it wasn't really necessary, but this interval is actually the range between negative infinity and 1. That's the lower limit of our interval. So for lower, now the only negative thing about this is that there is no negative infinity key in your calculator. So there's a workaround though. You're going to type in negative, and by the way, don't use the minus sign, use the negative, which is directly below the 3. It's listed as negative with parentheses around it. Then you're going to hit second. Then you're going to hit the comma button, which is directly above the 7. And then you're going to hit 99. And that actually represents negative 1.0 times 10 to the 99th power, which is not negative infinity, but it's awfully, awfully close. And in the window, it should show up as either minus E99 or possibly, depending on your calculator, minus 1E99. And that means the same thing. All right, so start with that. And then for upper, of course, you'll use the 1. You don't have to type 1.0, just 1 is fine. And if you notice, it assumes, like I said before, that you want the mean to be 0 and the standard deviation to be 1, which you certainly do. And then, of course, you hit that paste button or enter, whichever, depending on your calculator, and it should end up giving you the 0.8413. Okay, with a lot of extra decimals afterwards. So that will give you the result that you're looking for, 0.8413. Okay, so that was a less than or equal to probability. Now, what about the other cases? Well, because they're asking you for the lower and the upper limit, you do everything exactly the same. It's just a question of what's the lower limit and what's the upper limit. All right. So I'll give you a minute to catch up, and then we'll do another example, which is a greater than or equal to probability. All right, so what I'm going to do is, just to save a little time, I'm going to copy this slide and make a few changes. Let's change this to greater than or equal to 1. Okay, so what's going on here? So this time, remember, this goes all the way up to positive infinity. So your lower limit is 1. The upper limit is positive infinity. For that, everything's the same except leave out the negative. It's simply second comma 99, and that should show up in your window as either E99 or 1E99. Leave these the same, and depending on your calculator, either hit paste or enter, and guess what you're going to get? Well, that's not a surprise, because remember, before we just got through calculating this probability as 0.8413. So it stands to reason that this one has to be 0.1587. So really, it's just a question of making sure that the interval is set up correctly. So in other words, this is the equivalent of saying this. All right, so that's why, so this one is the lower limit. This is actually positive infinity. That's our upper limit, or at least it's as close as we can get. 0 and 1 are, and again, if you notice, these were already in there. They did not ask you, or you don't have to type those over again, because they're assuming that that's what you mean. If not, well, we'll certainly change it ourselves. All right. Now, what's next? Of course, now we have to try an in-between problem. So let's change this one. I copied it, of course. Just to save a little time. Oh boy. Sometimes this is quick and sometimes it's not. Erasing with this thing. Sometimes it's all one big box, and it's just unbelievable. All right, let's try this one. Let's try the probability that Z, see, sometimes it comes off so nicely. All right, Z is between 1 and 2. Now, I believe we've already done this one. Yes, we did a little while ago. So we already know the answer. It was 1359, if I remember correctly. Yeah, we did this one, didn't we? Oh, that's right. There's no point in wasting time looking for it. But anyway, so let's do this now. You can see how easy this one is, because there's no infinities this time. It's just literally the ranges between 1 and 2. Wow, it doesn't get much simpler than that. So when you plug in those numbers, you'll get 1359. There it is. Okay, now I'm going to show you some examples that are not based on the standard normal distribution. All right, so you'll see it's so easy. All right, let's try an example. What could it be? All right, I have an idea. All right, let's try this. All right, this will be a new example. Suppose that gas prices per gallon, of course, or I should say, I guess, dollars per gallon in the tri-state area are normally distributed with a mean of $3.39 per gallon and a standard deviation of, let's say, 20 cents per gallon. Compute the following probabilities. So imagine you drive into a gas station and you want to know what's the probability that X, when now X is going to be the price of the gas. Remember, we use Z for standard normal, X is for all the others. The probability that X is less than or equal to $3.22, let's say. For some reason, we want to know that probability. So what do? Well, this time, we're not using the standard normal. The mean and the sigma have to be changed. So this one, the mean is 339. We're looking at 322, which means we're going all the way down to negative infinity. So here for lower, we'll have negative second, comma, 99. The upper will be 322. And here we have to change these. The mean in this case is 339. And the standard deviation is 20 cents per gallon. All right, so it's not going to take too much longer, but you do have to pay attention to that mean and standard deviation. It's no longer the standard normal distribution. We can't assume anything. All right, so let's plug in those numbers. I've got 0.1977, let's say. All right, it's about 20%. There's a 20% chance that the price is under 322. Let's say that matters to me because I only have that much money in my pocket, enough to buy 10 gallons at that price. All right. Let's say I went to Vegas and lost almost all of my money, and now I've got to drive home, and that's how much I can afford to pay. All right. All right. Now let's try a greater than problem. What's the probability in part B that the price is above 350? Ooh, that's kind of pricey, but it's not impossible. No, it's not impossible. Okay, so I can leave those down there. What's changing is up here. Okay, we're looking for the probability that X is at least 350. Given that the mean is 339. All right, so the lower limit is 350. The upper limit is positive infinity, or second, comma, 99. And then the rest of these stay the same, which is kind of nice. And they'll keep staying there until you change them, by the way. It won't flip back to 0 and 1. All right, so we've got 3.50 as our lower limit. Second, comma, 99 is our upper. 339, 3, 2, and 20, yes. So for this one, I've got 0.2912. there's about a 29% chance that we'll have to pay at least $3.50 a gallon. All right, now let's try an in-between problem. How about this one? Let's say we want to know the probability that the price is between, let's say $3.20 and $3.40. Okay, so let's do this. Oh, sorry, that's not me. That's not 0 anymore. That's 339. So the range is between 340 and 320. So down here we'll put all right. So we've got 320 up to 340. The mean is it's still the same, 339. The standard deviation is 20.20. And so I end up with 0.3489. And you notice we're always rounding to 4 places. That's pretty standard. So basically, we've covered all the possible cases that you could be asked to do. You've got less than, greater than, in between probabilities. You've got normal distributions and standard normal distributions. That's it. That's all you have to know. So you can decide for yourself, for any problem you might encounter, whether you want to use the table or whether you want to use the calculator. Now, if you don't have a very advanced calculator, you can still use the table. That's not a problem. It's just a little extra work. Okay. But if you do have the calculator, you might as well take advantage of it because it really is quite a time saver, as you can see. All right, now we're going to do something a little different right now. We're going to use the normal distribution, but for a very different purpose. Now, I just want to remind you that remember when way back we saw, in fact, you know what I'm going to do? Let me go back and get yesterday's chapter for this. What I'm interested in is this graph that I created, the histogram for when pi is equal to 1/2 for the binomial distribution. This one, yes. We're going to bring it over here. And we're going to notice something interesting. If you look at this, the binomial distribution, if I had more bars, look what starts to happen. Well, all right, it's not perfect, but what you're seeing here is the idea that as the number of trials increases, the results more closely resemble those of the normal distribution. And in fact, if you were in a very advanced mathematical statistics class, you could actually prove that as n approaches infinity, the number of trials, the binomial distribution converges to the normal distribution. So because of this, we can use the normal distribution to approximate the results of the binomial distribution. Now, you're probably asking yourselves, why would we ever do this? Why not just use the binomial distribution? Well, this is helpful. Well, there are certain applications where this is helpful, but let me just show you one case where you might think, maybe that's a good idea. The normal approximation can save a great deal of time when we have a large number of trials with the normal distribution. For example, suppose a coin is flipped 1,000 times. What is the probability that the number of heads is between 450 and 550? Now, clearly, this is a job for the binomial distribution. But how much work is this going to take? Because look what you actually have to do. We could calculate this by using the binomial distribution to compute, and then you would have x equals 450 plus 451 equals 452 all the way out to 550. Okay, now this would require calculation of 101 probabilities, which then have to be added up. That could take a very long time, and the chances of making a mistake are enormous. I mean, absolutely enormous. So instead of doing this, if we only need an approximation, we can use the normal approximation to the binomial distribution instead. All right, now the two should be fairly close to each other under most conditions. It depends on how many trials we have and the size of the pi. But for the most part, the closer pi is to 0.5, the better will be. Oh, and the larger the number of trials, the better will be the approximation. Okay. Now, I do want to point out that this is not the only reason why this approach is important. We'll see in later chapters other ways we can use this, put this to good use. But here, let's just assume that we need to calculate a binomial probability, but rather than going through the trouble of calculating a large number of binomial probabilities, why don't we use this approximation? All right, so we're going to do some examples right now, but before we do that, I see that it's time for our morning break. And so when we get back, I would say that we can do the examples. All right. And then I think there will be time to at least take a peek at chapter 8, which, like I said, it's based on the normal distribution, but it's a very different, well, we're doing something very different. So it takes a lot of setup, but you'll see that ultimately we're just using the normal distribution. So it'll be good review. All right. So, all right, let's stop right here. Now, I just realized the other day, I've been leaving the recording running while we're on break. And I realized too that there's no real need for it. There's a little button here that says pause share. The only problem with pause share is that if I forget to turn it off when we get back, we won't have much of a recording. So, but I'm going to try it right now, and I'll try to remember. Now, when it comes back, you'll see that the color changes to yellow. That's meant to be a hint. Something's not right here. So when we get back, if I don't turn it back on, you can remind me. All right. I think it'll just be easier for people watching the recording to not have to cut through 15 minutes of wasted space. So I'm going to try this as an experiment today. Anyway, in the meantime, let's have our break. And when we get back, we'll dive back into this and do our examples. All right. All right, it's time. And I remembered. Okay. So, all right, let's do this. So here's an example of this. This is a classic binomial problem, but even though it doesn't require a lot of trials, we still can use the normal approximation. It's not quite as good when you only have a small number of trials, but let's just see how this works. So you got, let's say it turns out that of the entire population, 8% of all people have type AB positive blood. That sounds about right. In a class of 60 students, what is the probability that somewhere between 3 and 7 of them have type AB positive blood? Now, because this is the binomial distribution, and by the way, I just want to mention here that there are actually several different blood types that you could have. You could have O, you could have A, you could have B, and you could have AB, and then for each one, you can either be positive or negative. So you might think, well, how can this be the binomial distribution? So basically, the way we get around that problem is to say, all right, if we think of AB positive as a success, and that probability is 0.08, then what you can do is say, well, then anything else, by which I mean O, B, A, the others, equals failure. And so if X is the number of people with AB positive blood, then X is a binomial random variable. So even though there's technically more than two blood types, it doesn't really matter, because if we define the experiment properly, and we're only interested in whether a person has AB positive or something else, then X, which is the number of people with AB positive, then it still qualifies as a binomial experiment as long as the trials are independent. And that simply means these people are not related to each other. And the probability of success, meaning the probability of AB positive blood, is the same for everybody. Then we can still use the binomial distribution. All right, so that's the clever way of doing this. In other words, we don't need a separate distribution because there's all these other different blood types. So anyway, in our experiment, N is 8. Oh, sorry, N is 60 because there's 60 students in the class. And pi, the probability of success, is 0.08. So we're being asked to calculate the probability of getting between 3 and 7, which would require us to calculate all of these probabilities separately and add them up. Now, that's a lot of work. So even in a simple case, relatively simple case like this, we might be tempted to say, you know, why not just go ahead and use the normal approximation? It'll save us a lot of time. All right, so let's give it a shot. So how does this thing work? Well, there's a couple of steps that you might not have expected. It turns out that, yes, it's true that in the limit, the normal distribution, the binomial converges to the normal, but you're still going to get an error involved in doing this. So let's say, for example, this is the actual binomial distribution that we're trying to model. So here's the, the histogram for this distribution. So by using a normal curve to approximate this distribution, you can see that you're actually going to get some errors. Okay, in other words, like here, for example, all the space, we're overstating the true probabilities up here, but down here we're missing some of the probabilities, like over here. In other words, there's errors involved, and it can't be helped when you use a continuous distribution to approximate a discrete distribution. There's going to be some errors involved. So in order to minimize the size of these errors, we're going to use what's called a continuity correction. All right. And the word, what that means is that we're correcting for the fact that we're using a continuous distribution to approximate a discrete distribution. And it turns out that this continuity correction is surprisingly simple. It seems to work very well. What we have to do is take our interval, and then all we have to do is add a half to the upper limit and subtract a half from the lower limit. So this means approximately equal to. So we add a half to the upper limit subtract a half from the lower limit. And we're good. Now, I do want to point out, though, that if either of your limits is infinity or negative infinity, then we don't have to bother with this. Okay, adding a half to infinity still leaves us with infinity. So if instead of 3 to 7, we're looking for a 3 to infinity, then we don't need to bother with the continuity correction for the infinities. Here they're both constants, so therefore we add a half to the upper limit and subtract a half from the lower limit. Now, once this is done, we're going to convert this x into a standard normal random variable. But we're going to do it in a very interesting way. You might recall that for the conversion formula that we saw earlier, we can convert any normal random variable x into the equivalent standard normal random variable with the formula z is x minus mu over sigma. All right, certainly we've seen this before. But in our case, x is not normal, it's binomial. So what do we do about it? We have to make an adjustment for this. So if x is binomial, converting into a standard normal random variable, it's a little different. Now, what I do want to remind you is that with a binomial distribution, the expected value of x, which by the way, can also be written as mu, there's a special formula for this, n pi. All right, we saw this in chapter 5. For the variance, we have n pi 1 minus pi. And the standard deviation is therefore the square root of n pi 1 minus pi. Well, what do you suppose we're going to do? Our conversion formula is going to be, instead of z equals x minus mu over sigma, we will use z equals x minus n pi over the square root of n pi 1 minus pi. Because it means the same thing, but remember, these values represent the binomial distribution, the mean and the standard deviation. So this is our conversion formula. So that's the second difference between what we're doing here and what we have been doing in this chapter. All right. So first the continuity correction, and then use this formula to convert to a standard normal form. So for the example of the students, let's see, we were looking for 3 to 5. No, wait a minute. 3 to 7. So after applying the continuity correction, the lower limit becomes 2.5 because that's 3 minus 0.5. The upper limit becomes 7.5 because we're adding a half. And so what we need to do now is calculate. So let me just label this as part 1, the continuity correction. Number 2, we need to know n pi. Now remember, the number of students was 60, and the probability of having type AB positive blood was 8%. So that works out to be 4.8. So that basically tells us that in a class of this size, on average, we would expect to get 4.8 students with that type AB positive blood. Now, obviously, we can't have 4.8. It'll be basically 5, but this is the mean of the binomial distribution. And then we're going to compute the standard deviation. All right, so we need to do the continuity correction. And before we convert to a standard normal form, we calculate the mean and the standard deviation for the binomial distribution. Okay, so we still have to do the standard deviation. 3, compute. Sigma is the square root of n pi 1 minus pi. So that would be the square root of 60 times 0.08 times 0.92. And that's approximately equal to 2.101, let's say. And then finally, we're allowed to do our conversion. All right. So in other words, we're going to use that formula, z equals x minus n pi over the square root of n pi 1 minus pi. And we're going to convert it or apply it to this formula. Here we go. So this is the adjusted interval. So we're subtracting. Remember, we determined that the mean is 4.8. And the standard deviation is approximately 2.101. So you notice what I'm doing here. I'm subtracting the mean, and I'm dividing by the standard deviation. So the question is, what are these numbers equal to? Well, that means that we're looking for approximately negative 1.09 up to positive 1.29. All right, well, we know what to do from here. We've done it so many times. Let's go to the next slide, and you'll see that if you use the tables, you just go ahead and calculate the difference between these two probabilities. But we'll also use the calculators as well. Okay, so this is what we're looking for. And the graph looks like this. And so you can see what we've done here. We've got z less than or equal to 1.29 minus the probability z is less than negative 1.09. And if you look those up in the tables, you'll see that the difference between the two is about 7636. Now, if you use the calculator, you may get a slightly different answer because these numbers have been rounded to fit onto the table. All right, so why don't we try that? There we go. So we have let me type this. We have, as usual, second VARS, normal CDF, lower, upper, and then we have the mean and the standard deviation. All right, so the lower limit was negative 1.09. The upper limit was 1.29. The mean was 4.8. And the standard deviation was 2.101. All right, let's throw that into the calculator and see what we get. All right, negative 1.09. Oops. No, negative, I made a mistake on my calculator. Negative 1.09, positive 1.29. The mean is 4.8. The standard deviation is 2.101. And I end up with, oh, no, obviously I did something wrong. Hold on. Oh, I know what I did. Of course. No, I just realized I made a stupid mistake here. No, here we're using the standardized numbers. This is 0 and 1. We can do it with both forms. All right, let's do this. Sorry, that was my fault. I completely forgot. This is already in the standard normal form. So let your mu be 0 and your standard deviation be 1. And we end up with 0.7636, which, is exactly what we got from the chart. But what if we had done it this way? Suppose if we're using the calculator, we don't actually need that conversion formula. All right, so let me just mention that here. If we are using the calculator to compute this probability, we don't need the formula. Z equals okay, we can just do it directly. So let's see how that would work. So here's what we would do. Now remember, when we did the continuity correction, actually, let me just copy this. The interval that we were actually looking for was between 2.5 and 7.5. Okay, so these were based on the continuity correction. Oh boy, let me see if I got space here. There it is. But now the mean does have to be 4.8, and the standard deviation does have to be 2.101, right? So we should get something very, very similar here. Again, it really just comes down to how much rounding is going on. And so let's try that. 2.5 up to 7.5. The mean is 4.8 and the standard deviation is 2.101. And I'm getting 0.7638 this time. So using this approach, we got 7636. Here I got 7638. That's because there's less rounding going on. Because it turns out the actual probability is 7639. So you can see it did an excellent, excellent job. So you can rely on this, even with a relatively small sample size. The sample size doesn't have to be massive. Now, in fact, there's actually a rule of thumb that we can use to determine when this is likely to be successful and when it is not. So this is on the next slide. These are the two conditions which determine whether or not this is going to work. So if n times pi is greater than or equal to 5, now here we only got 4.8, but that's really close. And then n times 1 minus pi, well, clearly that will be well above 5. 555.2, that's not even close. Although we didn't quite reach the target here, you can see that we're pretty close. So that's why our approximation worked as well as it did. If these numbers are not even close to 5, then we should probably not use this approximation. So this was done with the actual binomial distribution, by the way. All right. So that was a good example of how we can use the normal approximation to the binomial experiment, distribution rather, and it came up with a pretty good result. And once you get used to it, you'll see that, you know what, the other option was to calculate, 5 different probabilities and add them up. Everything from, here it is. If you had to do these individually and add them up, it would have taken quite a while, and there would have been a very high chance of making a mistake. This way, you can speed things up a bit and come up with a very good first approximation to the true result. Now, by the way, I just want to point out that this was much more important in the days when we didn't have calculators or Excel or any of those wonderful tools. It's not quite as big of a deal now because it doesn't take that much more time to do this directly in Excel than to do the normal approximation, but it still is useful. The results are still very important, and it's interesting to see how we can use a continuous distribution to approximate the binomial distribution. And I just want to mention too that although we're not going to see this here, you can also use the normal approximation to come up with the Poisson distribution. So we can use it in either case. All right, now why don't we try to do the same data with 2 slightly different questions. This time I want to know the probability that the number of students is no more than 6. Now, once we convert this to the standard normal distribution, what we're going to do is rewrite this as (6.5). Now, we don't need the lower limit because when we convert this to the standard normal form, the lower limit will be negative infinity. So what we have to do next is convert this, remember, with z equals x minus n pi over the square root of n pi 1 minus pi, or x minus 4.8 over 2.101. And this is approximately equal to z less than or equal to 0.81. And if you look that up in the table, or if you use your calculator, you'll get approximately 0.7910. And it turns out the actual probability is 0.7980. All right. That's not bad. It's not perfect, but it's not bad. Now here, the approximation is a little bit further off because with the normal distribution, you're literally going all the way down to infinity. If you were actually doing this with a binomial distribution, the lower limit would actually be 0. So that explains part of the reason why the approximation is not quite as good as it was before. All right, now let's do the opposite approach. How about calculating the probability that at least 4 students have the type AB positive blood? So, all right, so at least 4. Now, by the way, this implies that 4 is now the lower limit. So if you rewrite it like this, it's more obvious. So with a continuity correction, I'm going to subtract oh, whoops, I wrote it backwards. I'm going to subtract a half now. Okay, so now in principle, this goes up to infinity when we do the normal distribution, but since the class only has 60 students, technically the upper limit is 60, but when we convert it into the standard normal form, that amounts to infinity. All right, so how do we do this now? We use our transformation formula. Oops. All right, so when we apply that here, let's rewrite it like this. I think it's easier. Z is greater than or equal to negative 0.62. All right, so either using the table or the calculator, this turns out to be about 7324. Here the approximation is off a bit. And again, that's partially because the upper limit, we're using infinity, whereas with the discrete distribution, it's actually 60. The correct value is 0.7171. So this one is off a little bit, but it's still not that bad. So it's an open question whether or not it's worth our while to do this, especially now, of course, that we have high-powered calculators, we have Excel, but there's still some useful benefit to be had from using this approximation. All right, so that's pretty much it for chapter 7. So now you're ready to do the 2 problem sets. What's next is chapter 8, which is an extension of the normal distribution, although we're using it for slightly different reasons. So let's at least introduce this chapter. I don't want to get too deeply into it since we have to wait until Monday to go back into it. But let's do that right now. Let's take a quick peek at chapter 8, and let's see what this is all about. All right, so let's see what's going on here. I opened this before, okay. So let's get 8 open here. All right. So this is a very important branch of statistics. We're going to focus our attention once again on samples. Specifically, we're going to be focusing on the sample mean. But before we do that, there's a few key definitions we need to look at. And by the way, I just want to mention that I keep reminding you that every discipline that uses statistics may go about it in a slightly different way. Because for one thing, we typically have different kinds of data. Just as an example of this, in biology and psychology, you can do actual experiments. With finance and economics, no, you don't normally have the ability to do actual experiments. So the type of data that you use is very different in economics and finance than in psychology and biology. So that being the case, the way you would choose samples is also very different. In fact, sampling is such an important area of statistics that if you were getting a graduate degree in statistics, you might find yourself taking an entire semester of just sampling techniques. Now, you don't want to do that here. No, that would be gross overkill. But it's important to be aware that there are different ways of choosing samples. The one that will stick with it is very simple. This is what we typically see in finance and economics. And that is the simple random sample, where we choose the elements of our sample from an underlying population in such a way that each element of the underlying population is equally likely to be chosen. How would that work? Let's say that I wanted to choose a random sample from this class. All right, so let's just try that one out. For example, suppose a class contains 16 students, and I need a random sample for whatever reason of 4. I could assign each student a number from 1 to 16 and then use a random number generator, it's called, which you can find in a program like Excel or a package like Excel, a random number generator to pick 4 numbers from 16. And so, for example, I could end up with 1, 5, 9, and 13. That means those are the 4 students that I've chosen for my sample. And so each student has a 1 out of 16 chance of being chosen. Therefore, this is a random sample. Okay, so I've got 16 students, each has a number from 1 to 16, and I use a program whose only purpose is to generate random numbers. In fact, you could probably find one on the internet. Let's see what's out there. All right, this one, oh, that looks like fun. All right, see? It's just randomly choosing numbers. So I would go through and pick 4 of them and write them down, and that's my sample. Look how easy that is. Now, it's theoretically possible to get the same number twice. If I do, I just throw it out and do another one. But the idea here is that everybody is equally likely to be chosen. Now, as opposed to, let's say, suppose instead that I go to the mall and I randomly choose. So, or how about this? Suppose that I go to the mall and give out free samples. I choose everyone who comes to my table and asks for a sample. That's my sample. Now, here you can see that I picked only people who are likely to walk up to a table and ask for a free sample. Now, not everybody is willing to do this. Some people are very shy about such things. So I'm not really randomly picking my sample here, am I? Sometimes in statistics, this is called a convenience sample because I chose everyone who wanted a free sample. In other words, they came to me. I didn't have to go to them. So it's easy, it's convenient. And for some types of applications like marketing, this might actually be a good way to go. But for economics and finance, this is a terrible way to go. We want to have some assurance that the numbers were really randomly chosen. Okay, so we don't like this idea. Now, there's another way we could do this. Suppose that I break up the class into freshmen, sophomores, juniors, and seniors. And then choose 2 from each group. Okay, this type of sample is not random. Because you can see what the problem is, that if I pick 2 freshmen, then I'm not picking any more freshmen. Whoever else is left is not likely to be is not going to be chosen at all. And so this is known as a cluster sample and is frequently used in psychology, but not business applications. So in other words, imagine an experiment is taking place where they want to make sure that they're asking about attitudes about different things, and they want to make sure they have a certain number of each group in the sample, a certain number of freshmen, sophomores, juniors, seniors. Then this makes sense for them. But for our purposes, let's say we're doing some experiment where we're observing how much each one spends on gas each week or something. Then for them, a random sample would be a much more sensible approach. And that's not what we're seeing here. So the random sample, the simple random sample, I should say, just means everybody is equally likely to be chosen. All right. So now here's a definition I want you to see. Parameter versus statistic. A parameter is a summary measure of a population, like the population mean and the population standard deviation. Now, we use this in chapter 7 as well, and 6, to represent the measure of a random variable. But like I said before, we use the Greek letters for both populations and random variables. It should be clear which is which, though. A statistic is therefore a summary measure of a sample, like X bar and S. Those are considered to be statistics because they're measures of a sample. And by the way, this is the first time we're seeing this word formally defined. We've been in the statistics class for quite a while now, and we've never formally defined the word statistics. Well, here it is. These are summary measures of sample data. That's all they are. How do you like that? Name another discipline where you don't define the name of the discipline in the first day of class. Well, this is that one. We never told you until now what the word statistics actually means. It's a set of summary measures of sample data. That's what it means. All right, so you notice the name of the course isn't parameters, is it? It's statistics, because that's the information that we normally have to work with. All right, now here's the thrust of the entire chapter. Imagine the following situation. Oh, all right, you know what we can do? Why don't we actually do this with our little program here? What I'm going to do is, watch this. Suppose that we randomly choose 4 students out of 16. All right, so let's do it. All right, and we get 5, 16, 14, and 10. Now we do it again. This time we get 1, 5, whoops, 13, and 2. And let's do it one more time, just to get the thrust of what we're doing here. So here, we get 16, 14. Oh, all right, we don't want 16 again. We'll just run it. Okay, 11 and 8. Now, what if I were to calculate the mean of each of these 3 samples? So the sample means are going to be different. I'm going to do it right now. Don't worry. This will only take a minute. The first one is 11.5. The second one is 5.25. And the third one is 12.25. So if I were to continue doing this, like for hours and hours, what you would discover is that for each sample that I draw, the mean, the sample mean, is likely to be different. So we can think of these sample means as a random variable. Okay, that's really the heart and soul of this whole chapter. The sample means themselves could be thought of as a type of random variable. And we know that a random variable has its own probability distribution. For a sample statistic, such as the sample mean, the probability distribution is known as a sampling distribution. Now, if we had time, and maybe we'll throw this into Excel and try this, we could keep running this experiment over and over and over again, and then we could create a histogram out of these means. In fact, maybe next time, I'll tell you what, maybe we can try it right now. It's not that late. We got a few minutes left. If not, we'll finish it up next time. All right, let's keep it simple. Let's say that we've got 10 students in the class and we want to pick 5 of them. All right, so here's what we have to do. Now, because it's Excel, this will be pretty quick. The formula we're going to use is called rand between. We're going to do it 10 times. Yeah, see, the problem is this one is allowing for duplications. I'll tell you what, let's just overlook that for right now. Let's just do a bunch of these. I don't know how many that is. What I really care about is the means. All right, now what I'm going to do with this information is organize it. I'll just stop it right there. Let's just keep 30 of them. Okay. Oh, no. What did I do? That's better. Okay. So I got them into a column, and now I'm going to sort them. And then what I probably should do is break them up into categories. For example, 3 to 4, 4 to 5, 5 to 6, and 6 to 7, and 7 to 8. You'll see why I'm doing this in a few minutes. Okay, so I'm going to use one of Excel's built-in tools. Okay, so what we're going to do now is hopefully create a histogram out of these. There it is. Okay, so that's the histogram. And you can see, even though I don't have a whole lot of samples, in a way, it kind of looks like the normal distribution, doesn't it? Well, it's a little off. But if we do this enough times, all these means will start to resemble the normal distribution. All right, so if instead of having 30 of these, I had 100, it would look a lot more normal. So what the thrust of this chapter is that the sample mean itself could be thought of as a normal random variable, which means that we can calculate probabilities. So here's an example where I could do with this. What if I said to myself, what is the probability that the mean GPA in this class is more than 3.5? See, now that's very different than asking, what is the probability that student X has a GPA of more than 3.5? Instead, I'm asking about the average of the whole class. And so this discussion will enable us to calculate a lot more different kinds of probabilities that are very useful in practice. All of it ultimately comes down to the normal distribution. Anyway, so I think that's going to be enough for now. We can start this again on Monday, and of course we'll have to sort of go all through it one more time. I know there's a lot here. Maybe I'll make up a more complex example here so you can really see what these numbers look like when we have more information. So, and then graph it in Excel so you can see how closely this resembles the normal distribution. All right, so now don't forget that for next Monday, you should do the chapter 6 and 7 problem set. And then I'll post pretty soon the sample midterm, which you should also look at too, because I'd like to go over it on Tuesday so that I can hand out the midterms, let's say on Wednesday, and you'll have at least a week to get them done. All right, I think that's a good plan, especially because don't forget, I mean, this is only a 4-week class. We're actually halfway through right now. So every day is like basically 3 or 4 weeks during the normal year. So we've gotten a lot done, but we don't want to get complacent either. So I'll see you all next Monday. All right. Okay, I'll see you then. All right, you're welcome. All right, bye.